Okay, we're problem number 2, chapter 21. So we have a light bulb rated at, so the power is rated at 60 watts. And it has an RMS, so VRMS is 120 volts. What is the peak voltage applied across the bulb? So the maximum voltage is equal to the RMS voltage times the square root of 2, or the RMS is the max divided by 2. So all you do is take the RMS and multiply it by the square root of 2. 120 times the square root of 2 is equal to 170. So it's 170 volts peak to peak. What is the resistance in the bulb? We'll use the RMS value there. So if you remember, power is equal to, in a resistive circuit, is equal to I squared R, or it's equal to V squared over R. So since we have voltage, let's use that. Actually, let's solve for resistance. So resistance is equal to V squared over the power. And we use the RMS value, both for the current and for the voltage. So we have 120 volts squared divided by the power, which is 60 watts. 120 squared divided by 60. So the resistance I get is 240 ohms. That seems awful high. So make sure I haven't made a mistake here. 20 volts. Well, it might seem big because the voltage is big, so I'm just going to pause for just a second. I need to get up my... Okay, so that's the right answer. Okay, so on the last question, does a 100-watt bulb have greater or less resistance than a 60-watt bulb? So let's see. So we have the resistance, oh, actually a 100-watt bulb. P equals 100 watts. So it's the same kind of deal. So the resistance is equal to the RMS voltage squared divided by the power. You're going to see that actually a 100-watt bulb has a lower resistance than a 60-watt bulb. So I get 144 ohms. So the answer is it has a lower resistance, if that was the question. Does it have a greater or less resistance? So what happens is even though the resistance goes up, if you compared the current for these two cases, so let's do the current for 60 watts. You would have current is equal to voltage over resistance. So you'd have 120 volts divided by 200 ohms. 240 ohms, which is 0.5 amps. And if you do the current in the 100-watt bulb, you get 120 volts divided by the resistance, which is 144 volts. At 144 ohms. So 120 divided by 144 is 0.833 amps. So the current increases, you have a higher current in the 100-watt bulb. And it always works that way with resistive elements. The lower the resistance, the higher the temperature that you get. Okay, so that's the right answer. Okay, so we just talked about resistors. So now we're going to talk about capacitors. So let's do 21-9. So it says we have a capacitor connected to a generator like that. And the capacitance is 4 microfarads. So micro is 10 to the minus 6. And it says we have a generator whose RMS voltage, so we have V RMS, is equal to 30 volts. And the current in the circuit is observed, so I RMS is equal to 0.30 amps. What is the frequency of the source? So omega equals question mark. I guess actually F is the question mark. Okay, so what is going on here? So if we think about it, a capacitor is one of the cases where you integrate the voltage. Actually, I think what you would do is you'd use the reactance of a capacitor, which is equal to, let me find the formula for that. So for a capacitor, it is equal to 1 over 2 pi f times C. So we have C, and what we know is that Ohm's law applies. So if instead of using resistance, we have the RMS voltage is equal to the capacitive reactance times the RMS current. So we can calculate the reactance. It's the RMS voltage divided by the RMS current. So that is 30 volts divided by 0.30 amps, which is going to be 100 ohms. So now, this is 100 ohms. We know that, so we can solve for F. Solve this equation for F. So what we'll get is 1 over XC times 2 pi times C. So the only thing we don't know, well, we know everything. So we know that the reactance is 100 ohms. We know 2 pi is 2 pi. We know the capacitance is 4 times 10 to the minus 6. And the units are farads. So the frequency is 1 divided by 100 divided by 2 divided by pi divided by 4 e to the negative 6. And so I get 398 hertz would be the frequency. And you can see as the frequency gets higher, the reactance gets smaller, and therefore your current would increase because you would get less effective resistance through the whole thing. Anyway, that was problem number what? Number 9. So let me just look at that. So we get 4 times 10 to the second hertz, which is 400 hertz, so they rounded off to 2 significant figures. So that is correct. Okay, this is problem number 11 in chapter 21. And it says, what must be the capacitance of the capacitor inserted in a 60 hertz circuit? So let's write that down. Frequency is 60 hertz. With a generator of 170 volts maximum. So let's say Vmax equals 70 volts, 170 volts. And to produce an RMS current output of, so I RMS is equal to 0.75 amps. So we have 2 relationships between voltage and current. They both use the reactance, the capacitive reactance. And if you remember, the capacitive reactance is defined as, let me make sure I get this right, for a capacitor, the reactance is equal to 1 over 2 pi f times C. And Ohm's law, modified Ohm's law, says that the voltage RMS is equal to the current RMS times the capacitive reactance. So but it's also true that the voltage maximum is equal to the I max times the capacitive reactance. So we could either convert the RMS current into maximum current, or we could change the maximum current into RMS voltage. So I think we'll just do the voltage. So the RMS voltage is equal to the maximum voltage divided by the square root of 2. So that's still matter. 170 volts divided by the square root of 2. I got to find my calculator. I found my calculator. So 170 divided by square root of 2 is 120. Let's assume 3 significant figures, so 120 volts. That's the RMS. So we can solve for the capacitive reactance. It's going to be equal to the RMS voltage divided by the RMS current. So we have 120 volts divided by 0.75 amps. And the values for reactance are the same as resistance. So we get 160 ohms. That is the units for resistance. Okay, now what we can do is we can solve for the capacitance, which is I think what they're asking for. Yeah. So all you have to do is solve this for the capacitance. The capacitance is going to be equal to 1 over 2 pi f times the capacitive reactance. And since we have all that stuff, it's just a plug and chugger. So we have 2 pi times 60 hertz, I think, 60 cycles per second, times 160 ohms. So 1 divided by 2 divided by pi divided by 60 divided by 160. And we end up with 1.66 times 10 to the minus 5. And the units for capacitance are farads. And we'll change this into microfarads. So if we multiply by 10, we'll get 16.7 times 10 to the negative 6 farads, which is the same as 16, let's round up to 17 microfarads. Okay, let me just check the answer. Okay, this is problem number 15, chapter 21. And it says we have an inductor connected to an AC power source. So let's go ahead and draw the diagram. So there's our inductor. There's our AC power source. It has an inductance L. This has some voltage as a function of time. Corresponding current as a function of time. It says an inductor is connected to an AC power supply having a maximum output voltage of 4 volts. So we'll say V max is equal to 4.00 volts. And the frequency is 300.0 hertz. What inductance is needed? So the question is, what is the inductance to keep the RMS current less than 2 amps. So we want the current RMS to equal 2.00 milliamps, which is the same as 2.00 times 10 to the minus 3 amps. So just like with a capacitor, we have this relationship between voltage and current. And the answer is that the voltage, again, you could do the maximum voltage is equal to the maximum current times the inductive reactance. Or you can do RMS. You just have to be consistent, so it doesn't affect the reactance. So in this case, we have the voltage at maximum and the current at RMS. So let's just change the maximum voltage to RMS. So the RMS is always less than the maximum. RMS stands for root mean square. So 4 divided by the square root of 2 gives you 2.83 volts. Okay, so now we can use this. Actually, that should have been VRMS. So we can solve for the reactance. So it's going to be equal to the RMS voltage divided by the RMS current. So the voltage is 2.83 volts. The current is 2.00 times 10 to the minus 3rd amps. And we'll get units of ohms, slight resistance. And so I get 1,420 ohms. Now again, that's not, ohms is not due to resistance, but it's due to the fact that because we have a frequency that you're going to be changing the magnetic field within this loop, changing the current, which changes the magnetic field, which is going to induce a back EMF. So the magnetic field that's generated generates a voltage in the opposite direction. So all we have to do is write down what the inductive reactance is, and it's equal to 2 pi f times L, so we can solve for L. It's x sub L divided by 2 pi f. So we just have to substitute. So we have a reactance of 1,420 ohms divided by 2 pi, multiplied by the frequency, which was 300 hertz, I believe. Yep, 300 hertz. $14.20 divided by 2 divided by pi divided by 300 hertz. And that gives us 0.753 henries. Those are the units for inductance, henries. For capacitance, it's farads. And you could say that's 75.3 millihenries by multiplying by 1,000. So let me just check the answer. This is problem number 15. Sorry, I keep pushing the wrong button. So they say it's 0.750 henries. Okay, so yeah, I'm not sure where they got 0 from, but I got 0.753, but close enough for government work. Okay, this is problem 16, chapter 21. So we're talking about inductors now, just by themselves. And what happens with inductors is the higher the frequency, the greater the di dt, which means that the greater the resistance to the flow of current. So I have an inductor with a little source, and it says the output of an AC generator is given by delta V is 1.20 times 10 to the second volts, so it's 120 volts, and it's sinusoidal, and the argument is 30 pi t, so omega is equal to 30 pi. Or you could say the frequency is equal to, is that right? Omega t. And frequency is 2 pi omega. So does that mean frequency is equal to 60 pi squared omega? Is that right? No, 60 pi. Yeah, 60 pi squared. That seemed kind of strange. It has a squared in there. But I guess that's what it is. Guess I'll find out here. Sine of omega t. Okay. Seems like that's what it's got to be. Yep. Okay. The generator is connected across a 0.5 Henry inductor. So L is equal to 0.5. Find the frequency of the generator. Okay. So what do we here? I just did that. Frequency of the generator is 60 pi squared. So whatever that is, 60 times pi squared is equal to 60 times pi, times pi squared, 592. That's revolutions per second. F is equal to that. Okay, just get the answers up here so I can check it as I go along. Oh, yeah, I knew something was wrong. I should have followed my instinct because it's instinct. So it's actually omega equals 2 pi f. So f is omega divided by 2 pi. So let's erase that. It's wrong. So the frequency is going to be omega, which is 30 pi divided by 2 pi. And so we end up with 15 hertz. Or actually, it's not hertz. Yeah, it's hertz. Okay. 15 hertz. Let me show you this right answer again. 15 hertz. Okay. Second question. The RMS voltage across the inductor. So the peak, the maximum voltage is 120 volts. So the RMS voltage is just that, is just the peak, the maximum, divided by the square root of 2. And that happens for any sinusoidal type relationship. So we have 120 divided by the square root of 2, which is 84.9 volts. So that's the RMS voltage. The inductive reactance. So the inductive reactance is just equal to 2 pi f times L. So we know 2 pi, we know f is 15 hertz, we know L is 0.500 henries, and so the reactance, the inductive reactance is 2 times pi, 2 times pi times 15 times 0.5. So we get X of L is equal to 47.1 ohms. We always have ohms for reactance. The RMS current in the inductor. So the RMS current by Ohm's law is equal to the RMS voltage divided by the inductive reactance. So we have the RMS voltage, which would be it would be equal to 84.9 volts divided by 47.1 ohms. Now give us amps. So 84.9 divided by 47.1 give me 1.8 amps. So that's my RMS current. The maximum current is equal to the RMS current times the square root of 2. So I'll take 1.8 times the square root of 2. I'm just going to increase it. And I get 2.5 amps. The average power delivered to the inductor. So the average power for an inductor is 0. So the average power for a resistor is a value. The average power to an inductor and the average power to a capacitor is 0. So they're trying to trick you there. Find an expression for the instantaneous current. So I of t. So because it's an inductor, it's di. You take the derivative of the current to get the voltage. So if we take the derivative of this, we should get the voltage. So this is an integral, and if this thing has a sign, the integral of the sign is minus the cosine. So you're going to end up with negative. You still have the voltage, the maximum voltage, so it's 1.2 times 10 to the second. But you divide by the frequency, which is omega, this frequency, times the cosine of omega, which is 30 pi t. So you've got to divide by omega, which is 30 pi. So if I take the derivative of this, the chain rule will give me 30 pi in the numerator, which cancels out 30 pi in the denominator. The derivative of the cosine is a negative sign, so the negatives cancel out, and you end up with the voltage. So let's see if... Okay, so let me check my answer here. Okay, the average power is 0. So they had 2.55 amps sine of 30 pi t minus pi over 2. So they put the phase angle in there. So that's okay. So what they did was, because the cosine and sine are out of phase, you get I of t. Now if you take 120 divided by 30 pi, 120 divided by 30 divided by pi. Okay, I'm trying it here. 120 divided by 30 divided by pi, you get 1.3. And then you have the sine of 30 pi t minus pi over 2. Is that right? That's what they have. So that's just another way of writing it. Actually, we got 2.5. How did that happen? We got like 2.6. So let me think about this. 30 pi. 20 divided by 30 divided by pi. Okay, hold on just a second. So what they're doing is they're taking the max, 2.5. It should still work out. That's why I'm a little confused. So So the maximum voltage is 120. So that should have worked out. So let me just pause for a second. Okay, yeah, my problem here is that I need to factor in the inductance. So I'm actually going to divide this by 0.5. 0.5 henries. And that'll give me 2.6 sine. So this I also should divide by L over here, 0.5 henries. So we got 2.6 times 30 pi times t minus pi over 2. And the final question is at what time after t equals 0 does the instantaneous current reach 1 amp? So what I need is 1 amp for this. So I should be able to just solve for t if I know what I'm doing. So what I'm looking for is for 1 amp is equal to 2.6 sine of 30 pi t minus pi over 2. So if I divide by 2.6, so 1 divided by 2.6 is 0.385. Then take the inverse sine. I get 0.3 inverse sine, and I need to do this in radians. Okay, good. So I take the inverse sine of 0.385, which is equal to 0.395. Then I add pi over 2. So plus pi divided by 2 is equal to 1.966. So t is equal to 1.966 divided by 30 pi. Which I get to be 0.021 seconds, or in milliseconds, it's going to be 21 milliseconds. Okay, let's see if we got the right answer there. 21 milliseconds. So there you go. That's the answer. Okay, so far we've talked about capacitors in AC circuits and inductors in AC circuits. Now we're going to talk about an RLC circuit, which means we're going to have resistance, inductance, capacitance. And we're going to do problem number 18. So it says that we have a sinusoidal input voltage, which is going to be equal to 80 volts. That's your peak voltage, or your maximum. The sine of 150 t. So they're going to have a waveform. The coefficient in front of t is omega. So we know omega is equal to 150. And it has units of radians per second. So we know that 2 pi f is equal to omega. So if you solve for the frequency, you'll get it's omega divided by 2 pi. So if we take 150 radians per second and divide by 2 pi radians per cycle, we'll take 150 divided by 2 divided by pi, it's 23.9 hertz. Okay, so that's our frequency. It's applied in an RLC circuit, so here's our circuit. We have a sinusoidal input voltage. We have, let's put the resistor first, since that's R. Then we have L, which is the inductor. And then we have C, which is the capacitance. C, L, Okay. So the way you solve these problems is you deal with the reactance. So you have the reactance due to the resistor, then you have the one due to the capacitor, and you have the one due to the inductor. So the resistance is just the resistor. So we have 40.0 ohms. Now for the capacitance, it's, let me go back and look at the book because I don't memorize it yet, 1 over 2 pi fc. Or it could be 1 over omega c. Since we're given omega, might as well just use that instead of, we went through this extra step. Well, we may use it, we may not. We'll just use 150 radians per second times capacitance, which is given in the problem to be 125 microfarads. So 125 micro is 10 to the minus 6. Okay, so that's microfarad. So we drop the micro and rewrite it. And let's go ahead and calculate that. So we get 1 divided by 150 divided by 125 e to the negative 6. So I get 53.3 ohms. Okay, then you have the inductive reactance, 2 pi f times L, or just omega times L. Again, I'm just going to use omega. So we have 150 radians per second times L, which is Henry. What's Henry here? 60 millihenries. 80 millihenries. So it's 80.0 milli is 10 to the minus 3 henries. So it should be around the same magnitude as the other things. So we have 150 times 80 e to the minus 3, and we get 12.0 ohms. Okay, so those, and we don't just add them. We have to use the phasor diagram. So I'm going to draw a phasor diagram here, and we'll draw the different vectors here. So the capacitance, which way does that go? I don't remember yet. So let me just go back and look at it. So what's my guess? So if you go to page 703 and look there, the inductance goes upward. So this is this. That's, we could say that's X sub L. And then we have the resistance, which goes this way, and that's 50. So that one's 53. The horizontal one is 40, so let's make this a little bit shorter. And then you have the capacitive reactance, and that is only 12. Well, actually, no, I got it the wrong way around. So this one's the big one, and this one's shorter. If I did that right, which one's vertical? Vertical is inductance. Okay, so let's click on that. Make that short. So that is X sub L, and that is X sub C, and this is X sub R. So we add these two together, and so ultimately you add these two together, then you square the resultant of these two vertical vectors and add them to the square of X sub R. So the total impedance is defined by the square root of R, which I'll just say is X sub R, squared plus X sub L minus X sub C, quantity squared. So all I have to do is just plug in the numbers now. And let's just move this. Let's move this over here because I want to be able to see my numbers. Okay, so there you go. So we get the square root of the 40 ohms squared, and we take x sub L, which is 12 ohms, minus x sub C, which is 53.3 ohms, and we square that. And so we square the ohms, we take the square root, we get ohms. So we'll have 40 squared plus 12 minus 53.3, quantity squared, and then we'll take the square root. And so it should be on the order of the ballpark of these, because it's going to be, well, it's hard to tell, it's going to be on the order of magnitude of these. So we get 57.5 ohms. So that's the combined effect on the final waveform. So the problem asks us, what did it ask us for? What is the impedance of the circuit? Well, that's the answer. The impedance of the circuit is 57.5 ohms. What is the maximum current in the circuit? Well, what is the maximum voltage first? Well, the maximum voltage is the coefficient in front of the voltage. So we go back here and say Vmax equals 80.0 volts. And we know the relationship between voltage and current and impedance. It's Vmax is equal to Imax times X, or actually in this case times Z, the total impedance. So what we're trying to solve for is the maximum current. So Imax is equal to Vmax divided by Z. So we take 80 volts divided by Z, which is 57.5 ohms, and we get so many amps. 80 divided by 57.5, oops, missed something up there. 80 divided by 57.5, and I get 1.39, so I'll round out to 1.4 amps. Okay, let's check the answer. So that was problem number 18. Sorry. 18, 57.5 ohms, 1.39 amps, which is what I got. I rounded that up to 1.4, but there were 3 significant figures, so it probably is more accurate to do that. Okay, this is our second RLC calculation. And we have, let's draw our circuit again. It's a series of a resistor, a inductor, and a capacitor. Okay, so the resistance of the resistor is 50 ohms. The inductor has a inductance of 0.100 henries, and the capacitor is 10.0 microfarads, so C is equal to 10 microfarads. They connect in the series, which is what we have, to 60 hertz source, so 60 hertz. The RMS current in the circuit is 2.75 amps. So the I-RMS equals 2.75 amps. This is find the RMS voltages across the resistor, the inductor, the capacitor, and D, the RLC combination. Sketch the phasor diagram for this circuit. So to find the voltages across each one of those, all we have to do is, because the voltage is the same through each element, we can find the RMS, and they ask for RMS. So the RMS voltage across the resistor is going to be equal to the RMS current across the resistor, which we already know is 2.75 amps, times the resistance. So let's go ahead and do that. So all I have to do is plug in 2.75 amps times the resistance, which is 50 ohms, And we get 2.75 times 50, which is 138 volts. Okay, now we go to the inductor. And so it's the same thing, except you take X sub L. So I could have used X sub R here, just use R. So what we're saying here is X sub R equals R. Here, X sub L is equal to 2 pi F times the inductance. So let's just plug it in, everything in. So again, the current is 3.75 amps times X sub L, which is 2 pi, times the frequency, which is 60 hertz, times X sub L, not times X, it's times L, which is 0.100 henries. So 2.75 times 2 times pi times 60 times 0.1 is 104 ohms. 104 volts, sorry. And the final one is the capacitance. So you have via RMS of the capacitor is IRMS times X sub C, where X sub C is equal to 1 over 2 pi F times the capacitance. So again, we can just plug everything in. So we have the current, which is 2.75 amps times X sub L, X sub C, which is 1 over 2 pi times the frequency, which is 60 hertz, times the capacitance, which is 10 times 10 to the minus 10 times 10 to the minus 6 farads. So I converted microfarads to farads. And multiply all that stuff out. 2.75 divided by 2 divided by pi divided by 60 divided by 10 e to the minus 6, and I get VRMS equals 730 volts. So make sure that makes sense. We just check those before we go on here. This is problem number 22, so I'm going further if I have got the problem wrong. Just a second. So, okay, I did something wrong here. So for the capacitor, oh, that's the reactance. I don't need to put the voltage in there. Why did I do that? Okay, so, well, no, I'm calculating the voltage. Hold on just a second. 138, 104, and 729. 138, 104, 7. Okay, so I'm okay. Okay, so we're good. They calculated the reactances, and I kind of folded them in. Okay, so now what happens is we have this phasor diagram. And I guess that's where it would have been good to maybe have it otherwise, but I think we can, yeah, I mean, phasor diagram can apply to the reactances or it can apply to the voltages, so I think we're okay. So I'm going to do it in terms of voltage. So you have the capacitance one going up, I think. Let me go back and check it here. It won't be too long before I remember what to do. So the capacitance is actually down. Okay, so we're going to, this is the inductance part. And which one was the big one? That was the one due to the capacitance. So this one's going to be fairly small. like that. And then the voltage of the capacitor is going to go this way. It's just going to be 730. And then the resistance one goes this way like that. So we add that to that, which should give us, it'll give us a vector sort of like that. So it's shorter than the original one. And then you'll take these two and draw the resultant vector right there. And that should give me the RMS voltage for everything, taking into account the phase differences. Okay. And the way you do that is use the same kind of formula. We'll say that the RMS voltage is equal to the square root of the one due to the resistance, which is 138 volts. We'll square that, and we'll add that to, we'll take the capacitance one, which was, the inductance one, which is positive. So that's this one right here, which was 104 volts. And we subtract the other one, which is 730 volts, and we square it like that. And so we do the calculation. So we'll get 138 squared plus the difference between 104 and 730 squared. Take the square root, and we'll end up with 640 volts RMS. That's this one right here. Okay, let me check here. 640, yep. And we'll just move down to the next part. Was that it? I guess that was it. Let me read the problem. I don't see any more answers in the answer book. So, sketch the phasor diagram. Okay, and we could have done that. This was using voltages. This is the current, direction the current's going in, same as the resistor. This is the inductor side. This is V sub L, and this is V sub C. But it could have just easily been, and this is also V sub R going in that direction, which is the same direction as the current. But it could have been reactances, the same kind of triangle. Okay, this is problem 29. Example of an RLC circuit. The diagram in the book shows something like this. It has an inductor, and it has a capacitor. And it says that there's points A and D where there's a, so you got A, B, C, and D. And it says a voltage, so an AC source with a maximum voltage of 150 volts is across this circuit. So it's just the usual series circuit, and the frequency of oscillation is 50 hertz. And the resistance is 40 ohms. So that's R. The inductance is 185 millihenries, and the capacitance is 65 microfarads. So if we were to convert L to henries, it would be 181 times 10 to the minus 3 henries, which would be 0.181 henries. And the capacitance would be 65.0 times 10 to the minus 6 farads, which would be, we'll just leave it as that. Okay, now what's going to happen? Here's the procedure as I see it. They're looking for RMS voltages associated with each one of these elements. So what we can do is we can first change this voltage maximum to the RMS value. And all you have to do is divide by the square root of 2. So that's the first thing to do. So 150 divided by the square root of 2. It's 106. Okay. Now, what we're going to do is we're going to put all these in together and find the impedance of everything. So the impedance, when you have a resistor, a capacitor, and a inductor and a capacitor, is to do this. It's just basically, since these are 180 degrees out of phase, you subtract one from the other, and then you get, when you get this, you get one leg of a right triangle. This gives you the other leg of the right triangle. Use the Pythagorean theorem to solve for the vector sum, basically. So we already know R, 40 ohms. We have to calculate the inductive reactance, which is 2 pi f times L. And our frequency is 50 hertz. And our inductance is 0.181 henries. 2 times pi times 50 times 0.181. 56.9 ohms. So that's the inductive reactance. Then you can do the same thing for the capacitor. It's defined as 1 over 2 pi f times c. So we get 2 pi times 50 hertz times c, which is 65 times 10 to the minus 6 farads. So 1 divided by 2 divided by pi divided by 50 divided by 65 e to the negative 6 is 49.0. And that also has units. That's x sub c. That is 49.0 ohms. So they all have units of ohms. And it looks like we're in the ballpark because these are about the same. Now, they don't have to be the same, but they just make problems that way so that something doesn't dominate the whole thing. So now you can plug those numbers in and calculate the total impedance of the three things together. So the reactance is from the capacitor and the inductor pretty close to each other. They don't cancel out exactly, but they're pretty close. 40 squared plus the quantity 56.9 minus 49 quantity squared, 1662, and then we take the square root of that, and so we get 40.8, which is not that much different than 40 ohms. So let me just check to make sure that's the correct answer before I continue. So that's problem number 29. Okay, 49, 41, yep, okay, everything looks good. So now what we're going to do is we're going to find the current, the RMS current, which is equal to the RMS voltage divided by the impedance. And the RMS voltage was 106 volts. Our impedance is 40.8 ohms. And when you divide that out, you get 106 divided by 40.8, which is 2.6 amps. Now, the key thing about the current is that the current through each element is the same. So once you know the current, then all you have to do is to find the RMS across each element is to find the voltage. So the RMS voltage across the resistor is just the RMS current, which is going to be the same for all of these calculations, times, in this case, the resistance. So you'll have 2.6 amps RMS times the resistance, which was 40 ohms. And we get 2.6 times 40, 30, actually it's 30. 40, it is 40. Okay, you get 104 volts. So the voltage RMS across the resistor is 104 volts. Now across the inductor, VRMS for the inductor, I just say L, stand for inductor, is again the current, 2.6 amps. Well, let me put it symbolically before I do it like this. It's going to be I RMS times X sub L. So the current is still 2.6 amps times the impedance of the inductor, which turned out to be 56.9. So we get 2.6 times 56.9. So I get 148 volts. So VRMS across the inductor is 148 volts. And then for the capacitor, it's VRMS for the capacitor is equal to the same current times the reactance for the capacitor. So again, the current is 2.6 amps. And we go back, we'll find it's 49 ohms. So we plug 49 into there. 49.0 ohms, and we get a voltage, 2.6 times 49, and we get 127 volts. Now the thing is that these are the RMS values for each one of these things. You can't just add them together because they're happening at different times. This one peaks 90 degrees out of phase with this one peaks 90 degrees out of phase with this one, and then these two are 180 degrees out of phase. So when this is positive, this one's negative. And that's why the RMS, well, the RMS voltage is 106 volts. So the RMS across the resistor is a little bit less, but the voltages across the capacitor and the inductor actually are higher. Okay, let's just check my answers here. So 104, 148, 127, 104, 127, and what did I say the other one was? 148, they got 150. Okay, this is problem number, what are we going to do? Problem number 31. Actually, let's do problem 32. So we have an AC circuit with our resistance and our inductance and our capacitance. So what do we have? It says delta V is equal to 90 volts. That's our peak times the sine of 350 T. And supplied to a circuit, resistance, capacitor, inductance in series. The resistance has a value of 50.0 ohms. The capacitance has 25.0 microfarads, and the inductance is 0.200 henries. Okay, it says find the impedance of the circuit, the RMS current in the circuit, and the average power. So what we know is that the Vmax for the whole circuit that's being applied is going to be equal to 90 volts. It's just the amplitude of the thing. So VRMS is going to be equal to this divided by the square root of 2. 90 divided by the square root of 2. 63.6. 63.6 volts. Okay, now what we're going to do is we need to calculate the impedance of the entire circuit. And remember, the impedance is equal to the square root of the resistance squared plus the the inductive part again. X sub L. We don't square those. We take difference, and then we square that X sub L minus X sub C squared. So we just have to figure out what these are. So resistance is easy. It's 50 ohms. X sub L is 2 pi F times the inductance. But 2 pi F is omega. So we know that 2 pi F, which equals omega, is equal to the coefficient in front of the T variable. So that's 300. So this whole thing is 300. So X sub L is 350. And that is radians per second times L, which is 0.200 henries. So the inductive reactance is 350 times 0.2, which is 70 ohms. So 70.0 ohms. Okay, then X sub C is 1 over 2 pi F times the capacitance. So again, 2 pi F is omega. Omega is 350 radians per second times C, which is 25.0 times 10 to the minus 6 farads. And so we get X sub L is equal to 1 divided by 350 divided by 25 e to the negative 6. And I get 114 ohms. So those are the three individual parts. So now we just have to plug those into here. So we have the resistance 50 ohms squared plus the difference between the inductive reactance and the capacitive reactance, and we square those. Then we take the square root of the whole thing. So 50 squared plus the quantity 70 minus 114 squared, and then we take the square root of that, and I get 89.3. So 89.3 ohms is the impedance of the circuit. Okay, so the RMS current, RMS, is just equal to the voltage RMS divided by the impedance. It's actually like a resistance to some extent. So we take the voltage peak, or the RMS voltage, which we go back here, find the 63.6 volts. We divide by 89.3 ohms. Ohm's law says that's going to give you current in amps. 63.6 divided by 89.3 is 0.712 amps. Now, the only power that's required is the power that's dissipated in the resistor. The rest of the power, the rest of the energy just bounces back between the capacitor and the inductor, so we don't lose anything in those. So the power is just going to be equal to I squared R. In this case, it's the RMS value. So we take 0.712 amps. We square that, multiply by the resistance of the resistor. 0.712 squared times 50. And so power is in watts, so I get 25.3 watts. Okay, so let's check the answer. This is problem 32. So they said the impedance is 66.8 ohms. What did I get? I got 89.3 ohms. Wonder what I did wrong. 50, 43, that looks right. Okay, what did they do here? Okay, let me just look at my calculator. I may have just calculated this wrong. 50 squared plus the difference between 70 and 114 squared. Take the square root. 66. Okay, I just made a calculator error. So this is actually 66.6. So let's change that. 66.6 ohms. 63.6 divided by 66.6. 0.955 amps. Put that in there, 0.955 amps. Square that, multiply by the resistance, 50 ohms. I get 45.6 watts. Okay, let me check it now. 45, okay. And they also asked you what the phase difference is, I think. Average power. RMS. No, they don't actually ask for it. To find the phase difference, you would look at this. So let's just answer the question. What is the phase difference between the voltage and the current? So you would take the arctangent of, so theta, the angle, is going to be the arctangent of delta y, which is this part. So you're going to end up with negative 44 divided by 50, which is the x. So we get the arctangent, inverse tangent of negative 44 divided by 50, and I get negative 41.3 degrees as the phase angle. Just check that. Yep, if they use that in there. They did it differently. Same answer. What they did was they said that the power was equal to I times V, and then you multiply it by the cosine of theta or something like that, which basically gives you the same result. Okay. Okay, we're going to do a resonance circuit. And I'm going to do number 39. So we have an AM band extends from approximately 500 kilohertz to 1600 kilohertz. And it says if a 2.0 microhenry, so let's put L is 2.0 times 10 to the minus 6 Henry, is used in a tuning circuit for radio, what is the extremes that a capacitor must reach to cover the complete band of frequencies? So the question is, what is the capacitance based on these frequencies? So what we saw was that there's a result here that says the resonance frequency, which we specify by f sub 0, is equal to 1 over 2 times the square root of LC. So all we have to do is solve for the capacitance. So let's square everything. So 1 squared is 1, so you get 4 pi squared times LC. So then we can move the capacitance up to the numerator here and move the frequency down. So we end up with 1 over 4 pi squared L times F0 squared. So now it's just a matter of substituting in the information. So let's say the capacitance for 500 kilohertz. We've got to remember to do the kilohertz. That's probably the hardest part. So we get 1 over 4 times pi squared times L, which is 2.0 times 10 to the minus 6 henries, times the frequency, which is 500 times 10 to the 6, 10 to the third hertz. So the kilohertz is thousands hertz. Okay. So you get 1 divided by 4 divided by pi squared divided by 2e to the negative 6 divided by, so I got to square that, divided by 500, the quantity 500 e to the third squared. So I end up with 5.0 times 10 to the minus 8 farads. So that's going to be, well, yeah, it's going to be, if you did it as microfarads, it would be a small number. So we want to go up to the next thing. So what is the next thing? Is it pico? I always forget. So hold on, just as a nano. I think pico is 10 to the minus 12th. I mean 10 minus 9th. So let me just, yeah, where do I find, how do I find this? I don't remember it. So I'll just look up pico. Pico. How about prefixes? Prefixes, metric units. 3T. What does that mean? 3T. Well, I think it was in chapter 1. They had all those different thingy-diggies. So yeah, look at table 1.4. And 10 to the minus 9th is nano, so it would be 50 nanofarads. 50 times 10 to the minus 9th farads. 10 to the minus 9th is a nano. So we'd say nanofarads. Okay, so that's at 500 kilohertz. And the only difference in the next one is using 1600 kilohertz. So 1 divided by 4 pi squared, 2 times 10 to the minus 6 henries times 1600 times 10 to the third hertz squared. The nice thing about this is the capacitors don't have to be that big and the inductors don't have to be that big for radio tuning, which makes it nice because, you know, making large capacitors is somewhat problematic as well as large inductors. Okay, so we take 1 divided by 4 divided by pi squared divided by 2e to the minus 6 divided by the quantity 1600 e to the third quantity squared. And so I get 4.9 times 10 to the minus 9th farads, which is 4.9 nanofarads. So that would be the range. 50 nanofarads to 4.9 farads. Okay, so that nanofarads. What problem was that? I've already forgotten. Number 39. Okay, so let's look at the answer in the book. 51 nanofarads, 4.9 nanofarads. I have succeeded again. Okay, we have one more resonance problem, number 42. So again, we have a series circuit. We have some kind of voltage current source, and through our resistor, through our inductor, through the capacitor, and back around. So it's all there in series. And the value is we have a 3 Henry inductor, so that's equal to L. C is equal to 3 microfarads, 3 times 10 to the minus 6 farads. And we have a 30 ohm resistor connected to a voltage RMS of 120 volts. Find the power delivered to the circuit when the frequency of the source is the resonant frequency, half the resonant frequency, 1/4 the resonant frequency, 2 times the resonant frequency, and 4 times the resonant frequency. From your calculations, can you draw a conclusion about the frequency at which the maximum power is delivered to the circuit? Okay. So remember that the power delivered only has to be equal to what is dissipated in the resistor. So all we have to do is find the RMS current for each one of those frequencies and square that and multiply by the resistance, and that'll give us the power. So the key thing is finding the current for each one of those. Remember also that the current, the RMS current, is equal to the RMS voltage, which we know, divided by the impedance. So why don't we make up a table? Well, let's calculate, we have the L, C, and R. So let's make up a table. And what we'll do, first we need to calculate the resonance frequency. So the resonant frequency is 1 over 2 pi times the square root of L times C. So let's go ahead and calculate the resonant frequency. So we have 2 pi square root of L, which is 3 henries, times the capacitance, which is 3 times 10 to the minus 6 farads. Okay, so 1 divided by 2 divided by pi divided by the square root of 3 times 3 e to the minus 6 power. And I get 53.1 hertz. Okay, so that's the resonant frequency. So what we need is a table, and we'll have a column with the frequency. We have how many frequencies? We have 5, I think. So we need six rows to include the headers. With the frequency, we can calculate the capacitive reactance, the inductive reactance. We have the resistance, and then we can calculate the impedance for the total thing, and then we can calculate the current, and then we can calculate the power. Okay, so that's the table. Hopefully I got everything in there I needed. Okay, so this is the frequency. So the resonant frequency is this. The first case was 1/2 the resonant frequency, which would be 53.1 divided by 2, 26.6, 1/4. So divide that by 2 again, which would be 13.3. Double 53.1 times 2 is 106. And then times 2 again would be 212. So those are the frequencies in hertz. So then we're going to have X sub L, X sub C, R, Z, I, R, and S, and power. So x sub L is equal to 2 pi f times L. So I'm just going to do these in my calculator. Just change the one number, 2 pi times the frequency, which is 53.1, times L, which was 30 henries. So I get 2 pi f times L. So I get about 1,000 here. Okay, so if I half the frequency, I'll get 500. If I have the frequency again, I'll get 250. If I double the frequency, I'll get 2,000. And if I double the frequency, I'll get 4,000. So those are the values. I just based it on the only thing that changes the frequency. Okay, so now we're going to try x sub c. That's 1 over 2 pi f times c. So we'll do it for 53, and then the opposite will happen. So we get 1 divided by 2 divided by pi divided by 53.1 divided by the capacitance, which is 3 e to the negative 6. And I get 1,000. That's why they chose those numbers. Okay, so when I have the frequency, I'll actually double. And then double it again, and then I'll have it, and I'll have it again. Okay, the resistance in all these cases is just 30 ohms. It's not very many. Okay, so I'm just going to check to make sure. I'm surprised these are that much bigger. But I will, let me just check the answer here. I might have made a mistake somewhere in my frequency calculation. So this is problem number 42. So the resonant frequency is what is the resonance frequency? They don't actually tell me. Wait a second, did I do something wrong here? 1 over 2 pi squared of LC. Yeah, that's correct. We all get the same numbers that I got. So, okay, looks like I'm right. Okay, we'll go back. So, just make sure everything looked okay. So, in this case, the impedance is just 30 because they subtract out. So you get 30. These cancel each other out, and the only contribution to the impedance is the resistance. Now, the second case, we have the square root of the resistance squared plus the difference between the, so I take 500 minus 2,000, and we raise that to the second power, close the parentheses, and so I get 1,500 here. And if I change one of these 250, and the other one to 4,000, I get 3,750. And the same thing is going to apply on the other side, just from symmetry. You've got the same two numbers, just you're going to subtract one from the other, but different. You'll get negative, but when you square it, you get the same thing. So we'll end up with 1,500 here and 3,750 right there. So now we can calculate the current. The RMS current is equal to the RMS voltage divided by the impedance. So in this case, we have the RMS voltage is going to be, it was 120 volts RMS, so we just take 120 divided by 30, and that gives us 4 amps, 4.00 amps. Then instead of dividing by 30, we divide by 1500. So our current gets considerably lower, 0.08, and then we divide by 3750, and I get 0.032. This will be 0.808. This will be 0.032. So because the current goes down, the power is all still through the resistor, but the current has gone down considerably. So we're going to have 4 squared times the resistance, which is 30 ohms. So I'll get 480 watts in this case, whereas the second case I'll have 0.08 squared times 30, which is 0.19 watts. And then I have 0.032 squared times 30, and I get 0.031 watts, and then these will be the same, 0.19 watts and 0.031 watts. So the maximum power is dissipated or is consumed at the resonant frequency. And let me just double check my numbers here. So I got 480 watts. So what I got? Okay. And then I get 0.08. Well, that's the current. Power is 0.19. Yep. And then at the other one I get power of 0.03 watts. So all of those, and then the other ones are exactly the same. And it says the power delivered to a circuit is a maximum when the RMS current is a maximum. This occurs when the frequency of the source is equal to the resonant frequency of the circuit. So that is all correct. So the resistance that we use for calculating the power is always 30. The difference is that if you go away from the resonant frequency, then the amount of current gets decreased. It gets decreased significantly. So when you take I squared times the resistance, the resistor, then the power usage is got down significantly for a given voltage. Okay, this is problem number 15, chapter 21. And it says we have an inductor connected to an AC power source. So let's go ahead and draw the diagram. So there's our inductor. There's our AC power source. It has an inductance L. This has some voltage as a function of time. Corresponding current as a function of time. It says an inductor is connected to an AC power supply having a maximum output voltage of 4 volts. So we'll say V max is equal to 4.00 volts. And the frequency is 300.0 hertz. What inductance is needed? So the question is, what is the inductance to keep the RMS current less than 2 amps? So we want the current RMS to equal 2.00 milliamps, which is the same as 2.00 times 10 to the minus 3 amps. So just like with a capacitor, we have this relationship between voltage and current. And the answer is that the voltage, again, you could do the maximum voltage is equal to the maximum current times the inductive reactance. Or you can do RMS. You just have to be consistent. so it doesn't affect the reactant. So in this case, we have the voltage in maximum and the current at RMS. So let's just change the maximum voltage to RMS. So the RMS is always less than the maximum. RMS stands for root mean square. So 4 divided by the square root of 2 gives you 2.83 volts. Okay, so now we can use this. Actually, that should have been BRMS. So we can solve for the reactance. So it's going to be equal to the RMS voltage divided by the RMS current. So the voltage is 2.83 volts. The current is 2.00 times 10 to the minus third amps. And we'll get units of ohms, just like resistance. And so I get 1,420 ohms. Now again, that's not ohms. It's not due to resistance, but it's due to the fact that because we have a frequency that you're going to be changing the magnetic field within this loop, changing the current, which changes the magnetic field, which is going to induce a back EMF. So the magnetic field that's generates a voltage in the opposite direction. So all we have to do is write down what the inductive reactance is, and it's equal to 2 pi F times L, so we can solve for L. It's X sub L divided by 2 pi F. So we just have to substitute. So we have a reactance of 1,420 ohms divided by 2 pi multiplied by the frequency, which was 300 hertz, I believe. Yep, 300 hertz. $14.20 divided by 2 divided by pi divided by 300 hertz. And that gives us 0.753 henries. Those are the units for inductance, henries. For capacitance, it's farads. And you could say that's 75.3 millihenries by multiplying by 1,000. So let me just check the answer. This is problem number 15. Sorry, I keep pushing the wrong button. So they say it's 0.750 henries. Okay, so yeah, I'm not sure where they got 0 from, but I got 0.753, but close enough for government work. Recording started. Okay, this is problem number 53, and it relates to the oxygenation of hemoglobin. And I'm going to read the problem and add a few editorial comments. So it says oxygenated hemoglobin absorbs weakly in the red, hence its red color, and strongly in the near infrared, whereas deoxygenated hemoglobin has the opposite absorption. So it passes light through your finger, and it looks at the absorption spectrum, specifically at 2 wavelengths, and looks at the ratio of those two. And the ratio gives a reading of how much oxygen is in the blood. If you've ever gotten to the doctor, a lot of times, especially in the hospital, if you're having surgery or something like that, they'll stick one of those things in your finger. You wonder what the heck it's doing. So they're checking to make sure your blood is oxygenated enough. Okay, so it says the device clips onto the end of a person's finger and has two light-emitting diodes. A red, which is at 660 nanometers. So let's call that lambda sub r, and it's going to be 660 nanometers. And a nano is times 10 to the minus 9th, so it's 600 times 10 to the minus 9th meters. And then we have the other one, which is, we'll call it lambda sub I, which is infrared, and it's 940 nanometers. So it's a longer wavelength. Infrared is longer than the visible. Ultraviolet is shorter in terms of wavelengths. And so just like before, we'll have 940 times 10 to the minus 9th meters. So the first part of the problem is just a simple matter of using the relationship between wavelength, speed, and frequency of oscillation. And that relationship is that the speed of light is equal to lambda times, so what do we got? We got a lot speed, wavelength, and frequency of the other one. Okay, so we can solve for whichever one we're interested in. C is always a constant for electromagnetic waves. C is equal to 3.00 times 10 to the 8th meters per second. And since I have meters here and I have meters per second squared, meters per second there, frequency is cycles per second. So cycle is not a real unit. It doesn't have any size to it. It's just oscillations. So it's inverse seconds, 1 over seconds. So if you take meters times 1 over seconds, you get meters per second. So we know we've done the equation. We've remembered the equation correctly. So to calculate the frequency, which is what they were looking for, I think, determine the frequency of these light sources. So the frequency of the red is just going to, if we solve for f, we divide, so we have c divided by lambda. C is 3.00 times 10 to the 8th meters per second. And we divide by the wavelength, which is 660 times 10 to the minus 9th meters. So let's put that in the calculator. 3e to the 8th speed of light divided by 660 e to the minus 9th. And so the frequency of the red light is 4.54 times 10 to the 14th hertz, which are cycles per second. And you can do the same thing for the infrared. Now, because the wavelength is longer, the frequency will be shorter. Is that right? If this is, well, actually, this is longer. So that if this is bigger, then that should be smaller. So the frequency will be lower. So again, we do C over lambda, but it's lambda sub I. I'll put I over here. Likewise here, we should have used lambda sub R. So we have 3.00 times 10 to the 8th meters per second divided by 940 times 10 to the minus 9th meters. So 3e to the 8th divided by 940 e to the negative 9. So the frequency is lower, 3.19 times 10 to the 14th hertz. So that's a pretty small oscillation frequency. So you have basically almost 14 whatever 10 to the 4th is, oscillations per second in terms of the wavelength. Okay, so that's part A. Part B is talking about energy, and it says if 67% of the energy of the red source is absorbed in the blood, by what factor does the amplitude of the electromagnetic wave change? So then it says, hint, the intensity of the wave is equal to the average power per unit area as given by equation 21.8. So let's go look at that. Or was it 21.18? 21.18, I'm pretty sure that's what it says. Let me go back here. 21.28. Okay. So if we write that equation now that they suggested, the intensity is equal to the maximum magnetic field squared divided by 2u0c, or c divided by 2u0 times the magnetic field maximum. Okay. So let's read it again. So it says if 67% of the energy and I is the average power per unit area, so it says that the intensity is equal to the average power per unit area. Okay. So just hold on a second. I'm thinking.
Recording started.
Okay, so this is the amplitude. We're having a variation in the electrical magnetic field. And so this is E max, would be the distance from the average value to the peak. And these are all constants. So if we wanted to look at how say we started out with some initial intensity and we divide it by the final intensity, if you take the ratio of these two equations, the constants cancel out. And so you get E squared max initial divided by E squared max final. And so in the problem, what they're saying is that the amplitude, they're saying the energy decreases by 67%. So if it decreases by 67%, what's left over, the intensity final, is equal to 1 minus 67%, which in decimal form is 0.67 times the initial intensity. So the final intensity is 0.33 times the initial intensity. And if you take the ratio of those two, what you find out is that I initial divided by I final. Let's see if we want to do that. We would divide by that, which would give us 3. So I initial over I final is going to be equal to 3. So we divide by this and divide by that. 1 over 0.33 is approximately 3. So we get 3. So the ratio of the maximum value here is going to be related to this, but you take the square root to get that. Okay, because if they're squared, they would end up being. So if we wanted to find E max, let's do this by E max final over E max initial. I'd change the numerator to the denominator. Is going to be the square root. If you take the square root of both the numerator and the denominator, you get I final over I initial, which is, this is a reciprocal of that, so we would get the square root of 1/3. And if you take the square root, or square root of 1 divided by 3 is 0.57. So that would be the ratio of the amplitudes of the magnetic and electric fields. So it's the same ratio, whether you're talking about magnetic fields or electric fields. So the magnitude, the peaks would decrease by approximately 43%. The power would decrease by 67%.
Recording started.
This is problem number 59. And what we have is a short problem. The eye is most sensitive to light of wavelength 5.50 times 10 to the minus 12 meters, which is in the green-yellow region of this visible electromagnetic spectrum. What is the frequency of the light? So it's this relationship, C is equal to lambda times F, that we use. So we're given lambda in this case. Lambda is 5.50 times 10 to the minus 7th meters. C is always the same, 3.00 times 10 to the 8th meters per second. And so if we solve for the frequency, which is what they're asking us for, it's just going to be equal to C divided by lambda. So we have 3.00 times 10 to the 8th meters per second divided by 5.50 times 10 to the negative 7th meters. And so the final answer, which is going to be in cycles per second or hertz, is 3 e to the 8th divided by 5.5 e to the negative 7th. And we get 5.45 times 10 to the minus 14th hertz cycles per second.
Recording started.
Okay, this is problem number 60. It says a diathermy machine used in physiotherapy generates electromagnetic radiation that gives the effect of deep heat when absorbed in tissue. I think I had one of those once. Went to a chiropractor for my shoulder pain. But anyway, what is the assigned frequency for diathermy? One assigned frequency for diathermy is 27.3 megahertz. What is the wavelength of the radiation? So again, this is just using this relationship. C is equal to lambda F. In this case, they are giving us the frequency and not the wavelength. So the frequency is 27.33 megahertz. And megahertz is times 10 to the 6th, so we have 27.33 times 10 to the 6th hertz, which is the base unit for frequency. Again, it's an electromagnetic wave. Okay, sorry for the interruption there. My wife came by to have lunch with me since she was off today for school. So we were on problem number 60, as you already know, because you didn't have an hour break like I just did. Okay, anyway, so this is the frequency, 27.33 megahertz, 10 to the 6 hertz. And so the speed of light, or the speed of really electromagnetic waves, is 3 times 10 to the 8th meters per second. So all we're trying to do is find out the wavelength. So lambda is equal to C divided by F, just by solving for that. So we have 3.00 times 10 to the 8th meters per second divided by 27.33 times 10 to the 6 hertz. And before we actually do the calculation, if you remember in class the other day, we looked at FM signals, which were something like 100 megahertz. And so that was a couple of meters, I think. So this should be somewhere around the same thing on the same order of magnitude. So we have 3e to the negative 8, positive 8. 3e to the 8th divided by 27.33 e to the 6th. So we get that lambda the wavelength is 11.0 if we round off to 3 significant figures. 11, just 11. Okay, so that's meters. So that's quite long, and that makes sense because we were talking about 100 megahertz, so this is about 1/4. And so 1/4 the frequency, which would be 4 times the wavelength. So that's about what we were thinking it would be. Problem 61, another short problem. So this is on page 730. What are the wavelength ranges in the AM radio band and the FM radio band? So we're given the frequencies. So really all we have to do is we just have to write these out. AM goes from 540 kilohertz, which is equal to 540. Kilo is 10 to the third, so we get 10 to the third hertz. So let's just go ahead and calculate it. Lambda is equal to C over, what do we have? Frequency. So we get 3.0 times 10 to the 8 meters per second for the speed of the electromagnetic waves. Frequency is 540 times 10 to the third hertz, which is inverse seconds. If we do that calculation, we're going to get a fairly long wave. It's just because the speed is so high. 540 e to the third power kilohertz. So we get 556 meters. And in some ways, you could just take these if you wanted to find the other one. So because the speed of light remains constant, all we'd have to really do is, if we wanted to find it at 1600 kilohertz, all we'd have to do is take the ratio of 16 to 5, and actually it's the other way around, 5 to 16. So 5.4 divided by 16.0. So that's where the 5.4 comes from, and the 16, or you could say, 0.54 or over 1.6, doesn't really matter. And then you multiply by the wavelength, the wavelength at 540. Because what's going on here is if you have C is equal to lambda F, if C is a constant, then you could say lambda 1 F1 is equal to lambda 2 F2. And so if you solve for, so you have the product of the frequency and the wavelength divided by the new frequency. It's going to reduce the wavelength. Okay, so 5.4 divided by 16 times 556. I get 188 meters. So that's the range, 180 meters to 55.6 meters. Now, AM stands for amplitude modulation. So basically what they're doing is they are sending the signal at a certain frequency, and you tune your radio to that frequency. And then you'll get a signal. So at that frequency, you filter out all the other frequencies, and you'll get some signal that's like this. Okay. But the frequency is always the same, it's just the amplitude varies. So what then you do is you take that amplitude, so the maximum values. So if you just took the maximum values of those things as a function of time, so you would, you might do something like this. So you can take that signal, and that signal would be related to the signal that you're trying to transmit. So it would be looking at the peak values, and you take the peak values and represent that as, so this would be like amplitude. This would be the actual signal, which is varying at these wavelengths and these frequencies. Okay, so that's how amplitude modulation works. So the frequency, the wavelength's not that super important. Really what's important is that you have enough for oscillations per second that you can then take those peaks and come up with a signal that makes sense. Okay, the second set was FM. So let's go ahead and calculate it at the smallest, lowest frequency. So we have 88 megahertz. And so that's 88 times 10 to the 6 hertz. Mega is 10 to the 6. So if we calculate the wavelength associated with that, we just take speed of electromagnetic waves divided by the frequency, which is 88 times 10 to the 6 hertz. And the resulting, we'll get meters. 3.0 e to the 8th divided by 88 e to the 6. So we get wavelengths of 3.41 meters. And you can do the same thing as we did before. If you take the ratio of the second frequency, so if we take 88 divided by 108, and we multiply by the wavelength, 3.41 meters, at the higher frequencies, the wavelengths become smaller, so that's why we stick the bigger number in the denominator. So you get 88 divided by 108, and we get times 3.41, and so we get the second, the longer wavelength is 2.78 meters. So that's the one associated with 108 megahertz. This is the one associated with 88 megahertz. Now, FM stands for frequency modulation. So actually the data is in the frequency varying the frequency as a function of time. Where here you have a constant frequency and you vary the amplitude. So if when you tune into a FM station, a lot of times, you don't have to be exactly on the frequency to get a signal. And so that slop in either side of the target frequency, the average frequency, is where the information is held, not in the amplitude. So if you have this signal, it's not so much the amplitude variation. So if you have noise from some sort, which is affecting is usually going to affect the amplitude, then it's not affected as much. The frequency is not affected by noise or extraneous influences. And so, the better quality sound is in FM. The problem with the shorter wavelength is that it doesn't travel as far. So you have to have your transmitter closer to where you're transmitting to. Whereas AM stations, especially in the evening, can go tremendous distances. And you guys have never experienced this, but back in the 60s or 70s, you could turn your AM radio on and get signals from Chicago or New Orleans, and there would be no way that would happen with FM. It just wouldn't get over the topography and the curvature of the Earth. And we were talking about shortwave radios the other day. That's another reason why shortwave radios have the wavelengths that they are, because they end up bouncing the waves off the one of the atmospheric layers. So that's how you get signals to go around the curvature of the Earth. It's like inside a pipe, and a big pipe, if you threw it and hit the wall, it would bounce off the wall, and then bounce off the wall on the other side, and bounce back and forth, and it would finally get down the pipe. And so, even if you have a curved pipe, it would work that way. Whereas if you tried to throw it right down the middle, it only worked for a straight pipe. So that's kind of the idea of shortwave radios and the wavelengths. Okay, that's it for that one.
Recording started.
This is the final problem in this section. And it's, of course, you can see if you look at it, it's blue, so it's not as easy as the other ones. So let's read it and see what it says. The Number 62. An important news announcement is transmitted by radio waves to people who are 1,100 kilometers away. Sitting next to their radios and by sound waves, okay, so they're sitting next to the radios. By sound waves to people sitting across the room 3 meters from the newscaster. Who receives the news first? Explain, take the speed of sound in air to be 343 meters per second. So basically, you have some guy here with a microphone. And it goes to an antenna here. So here's the antenna going plus or minus. Transmits an electromagnetic wave to another antenna, converts that to electricity, goes through a receiver here, so there's a receiver, and the person's ear sitting right next to the radio. So that's going to take a certain amount. We're going to assume that it doesn't take any time to get from his mouth to the microphone here. And then in the same room as this microphone, you got somebody over here just sitting, here's their ears, and has to go through sound waves. And so that's going to take a certain amount of time. This is within the same room as the microphone. So here's the room, whereas this is, of course, not drawn to scale. This distance is 100 kilometers, and this distance is 3 meters. So the question is, who hears it first? Does this guy who's in the same room, but it has to go through sound 3 meters, or does a person who has their ear right next to the radio, so he hears it immediately? The only delay is this distance. As far as the, so basically we have to figure out the time. How long does it take to go this direction? How long does it take to go that direction? Well, the relationship between time and velocity is the same. So velocity is let's say, distance divided by time. So if we solve for time, time is distance divided by velocity. So here we've got a long distance, but a much higher velocity. Here we've got a lower distance, but a lower velocity. So let's do with sound. Let's check that out. Sound. Time is equal to distance, 3 meters, divided by 343 meters per second, which is the speed. So we get 3 divided by 343, and it's going to be 0.0087 seconds, which we can round it off to use scientific notation, 8.7 times 10 to the minus 3 seconds. Okay, then radio, which means electromagnetic radiation. The time is the distance, which is 100 times 10 to the third, 100 kilometers, a thousandth of a kilometer. Again, that's meters. So 100 kilometers is 100,000 meters. And we divide by the speed, which is the speed of light, or the speed of an electromagnetic wave. So we take 100 e to the 3 power divided by 3 e to the 8th power. And we get 0.0, actually, it's already in scientific notation, so on the calculator, you get 3.3 times 10 to the minus 4 seconds, which is the same as 0.33 times 10 to the minus 3 seconds. So obviously it's going to take a lot less time, almost by a factor of 20, shorter to go by radio. So we're going to say the radio person, which, first thought you think is crazy, but in reality, and it's not a huge difference here because, you're talking about milliseconds, so it's not like anybody would ever notice the difference, but it's a question they have asked. So let me just take the answer on this, and then I'll let you know if we get it right.
Recording started.
Okay, so that's correct for that particular problem.